let's get started. We're trying to finish regression and move to a topic that is called model selection and the idea of cross-validation and error decomposition. So just a note, homework 1 solutions are available now. Right here up front, you can take it on your way out. The project proposal. So, can you settle down? So a lot of you are working on your proposals, and I thought I'd show you this one proposal that was. This was for the class, but Igor is also working. Igor here. Anyway, this was for the class, but Igor is also working on his master's thesis research. It's structured according to the class proposal, so I wanted to run this by you to show you what we kind of expect. This is over the page limit. We give you a sort of rough of 2 pages. This is 5. If you want to exceed, that's fine. Our expectations were 2, but I want to run you through the kinds of things that Igor is going to be working on. So he's listed out that he wants to do visual-based object tracking. He writes out exactly what sort of coordinate frame he's going to be working on, what the problem is, what the problems are. He has a proposed method in mind. It's called the dagger algorithm. He's cited it here. Here's the algorithm that he's written down. He's read that paper already. He has some idea of vision techniques that he's going to use. He's written down what sort of software he's using. A Parrot AR2 drone will be used for this project. Here's what it has. Here are all the sensors that the thing is equipped with. Here's a library that he's going to use to fly the drone and to access the sort of camera on the drone. And here's a sort of detailed timeline about what he's going to be working on, broken down into weeks. We only asked you for your midway project. What is your milestone? But for your own purposes, it would be useful if you in your head, it's a useful exercise to sort of write down what you expect at various weekly checkpoints. I'm not going to be checking those checkpoints, but you know that you're behind your head. Okay? Just a note about this is kind of the things that this is a good project proposal. It doesn't have to be 5 pages, but these are the kind of details that we're expecting.
A quick question. So is the abstract during this proposal or not?
No, it's not. It's abstract is not necessary, especially since you're putting all the details in the text.
What if the project is too greedy, let's say? Can it be change that?
We expect you to do some research now and look into things. So if you say, I will look at method X, Y, and Z for problem A, and method X, Y, and Z just doesn't apply to problem A, that's a problem. You should have looked into that now so that you know what the method is. You're not expected to know if there are some techniques that we're covering later on in the semester. You're not expected to know what the technique is or what the details are, but you're at least expected to know what the input and output of the system is. But yes, somewhat changes in flexibility is possible. Okay. And homework 2, you should already be working on it. Hopefully some of you have made progress. It's due whenever it's due. The Kaggle link was released and we sent an email out about that. Any questions about administrative things? Yes.
I just have a question now. For the competition, right? You only have 2 options. So how is the winner? There is a leaderboard for that.
There is a leaderboard. Yes, there are 2 options, but there are 2 options per test data. So the number of possible, you could think about enumerating it, but if I forget what is the size of the test set. Has anybody looked at it? There's 100 senators. We may have given you 40 in the test. 40 is still a large number. We're not going to be able to enumerate it. Okay. Alright, so here's where we were last time. So we were looking at linear regression, and we had talked about here's the model class, which is a linear model. We're going to learn a weight vector, which is the coefficients of this linear model. And at test time, we're going to learn them by minimizing a least squares criteria. At test time, we're just going to look into that model class and make a prediction. And we had set this up as a least squares problem. So we had defined a data matrix or a design matrix, where on each row of this matrix was a data point, right? So the first coordinate was always 1, that's the bias feature, and then you have sort of d coordinates, 1 for every data point, so n rows, d plus 1 coordinates. And we had written down squared loss in terms of these matrix coefficients, so you had written down the loss matrix, you plug through first order calculus, take the derivative, set it equal to 0, and you get this sort of an expression. But the ordinary least squares, the optimal thing to do is to compute the pseudo-inverse. So this quantity was the pseudo-inverse, multiply that by the predictions, the ground truth given to you in your training data set, right? And we told you that in MATLAB, this is as easy to implement as this, right? This is the design matrix, this is you augmenting one column, there's a pseudo-inverse call, and that's it. This is all of least squares regression. There's not much to do. And similarly at test time, there's not much to that either. Okay? And we had talked about this one particular concern, that this matrix right here may not actually be invertible if you don't have enough data. So if you measure 10,000 things about each instance and you only have 2 samples, this matrix is not going to be invertible because it just has rank 2 if you have 2 samples, at most rank 2. Okay? And that's going to be relevant today because we're going to make certain connections. Okay. The question that we then asked was, why are we dealing with squared losses? And we made the connections to Gaussians. And the connection specifically was that there is, here's your error model, that the output that is given to you is actually a function of the input, and this is just linear, W transpose X, plus some noise, and that noise is zero mean Gaussian. Right? This is a generative model, this is how the data was created, this is what you're assuming. And you can create new data according to this model if you can specify the weight parameter and this standard deviation parameter. Right? But our goal is not creating new data, our goal is fitting the mean parameter so that we can explain the data in front of us. Okay? And we said, okay, let's write down the likelihood function and let's maximize the likelihood of this model to find this parameter. And it turned out that resulted in minimizing these squares. Okay? So it was due to this expression right here. You have exponent of negative squared in the Gaussian. As soon as you started doing log likelihood, this term came out. You're trying to maximize, this became an argument. And so this is essentially why squared losses are related to Gaussian. Maximum likelihood estimation under the Gaussian noise model, Gaussian likelihood function is the same thing as ordinary. And we talked about the fact that a Gaussian doesn't place enough mass on its tails. It decays very quickly, and therefore what you end up with are non-robust estimates. So if this is your data set, these points, and you have clear outliers in your data set, the red line is what the least squares estimate is going to be. It's because every time you make a fit, the outliers are multiplied by the squares, and so their contribution to the sum of squares is a log. Right? And if you can, this is what that is showing. So this is the squared loss, and this is the blue line is the absolute loss. Sum of absolute distances of these points to the fitted line. And it's because it doesn't grow quite as rapidly as the squared loss that you can actually have a better fit. It's more robust to outliers. That makes sense? So in terms of probabilistic estimation, we changed the likelihood function from Gaussian to Laplacian. In terms of a loss function, we changed the loss function from L2 to L1. That connections. Okay, so here's what we want to do today. Now that we've made this clear connection between a probabilistic model for regression and a loss function for regression, and the fact that those two are equivalent, we'd like to go ahead and what comes next in probabilistic estimation? Bayesian estimation, right? You can put priors on the weight parameter. And what happens to the right side? What happens to the loss view of things when you put a prior? That's what we'll look at today. We'll also do polynomial regression and talk about error decomposition and model selection. Okay? Okay. So let's do that. So here's the sort of simplest sort of Bayesian estimation outline that we're going to have, that your likelihood function is still going to be Gaussian. Notice it has not changed to Laplacian. Right? We've gone back to the Gaussian stuff. But this time I'm going to put a prior on the weight vector. And that prior incidentally is also going to be Gaussian. And then I will ask for the maximum a posteriori estimate of the weight vector. Okay? So let's So here's the likelihood function. This is what we were working with. This just means that, once you fit a line, I actually just, this is the equation of the line, and I'm going to sample around that line, right? The errors are zero mean Gaussian. What I'm also going to do, this is the likelihood function. What I'm also going to do is define a prior. What sort of lines are plausible, right? Because this is, the likelihood function was just saying there is some line W transpose X equals 0, and what I do is I assume a Gaussian around it, and that's what gives me a noise, and that's how I get a point X over Y. And that's how I sample this point. The prior is going to be also in this case some Gaussian, zero mean, and it's a multivariate Gaussian. To keep our notation easy, what we'll do is we'll just say that this is equivalent to the fact that each coordinate Wj is, so this is a univariate Gaussian, this is a multivariate Gaussian, I is an identity matrix. We're going to not deal with multivariate Gaussians, we're just going to assume the coordinates are independent. Right? So IID coordinates of W. Right? Remember, W is a weight vector, W0 all the way to WD, and we're going to say each one of those coordinates are IID, and each one of them come from some Gaussian distribution. Okay? And they all have in each of the coordinates, they all have the same standard deviation, the same variance. Okay. So after that, we've done this many times. We have to do map estimation of what do I believe about these parameters now that I observe a data set, or arg max of log probability, and we know that we can convert this into arg max of log likelihood given W plus log probability of W. Right? You apply Bayes' rule to that, D given W times the prior divided by the normalization constant, that disappears because it's just limited. Okay? So far so good. Let me write that here. We've already done this, and so this is just going to be a couple of steps. We know that this becomes negative yi minus W transpose xi from our last time notes. Right, there was a log here, right? It's 1 over root 2 pi sigma squared e to the negative yi minus W transpose xi squared by 2 sigma squared, right? You take a log, the product, because of this, becomes a summation. I get that term, minus n over 2 log 2 pi sigma squared. Some normalization constant, doesn't really matter. Okay? So that was the first term. We already know how to handle that. The second term is going to, it's just another multivariate Gaussian. Right? It's just another Gaussian. And so this is probability of W is equal to product from j equals 0 to d, 1 over root 2 pi p square e to the negative wj squared by 2p squared. Right? Just the definition of, there are IID Gaussians, I'm just multiplying them together because they're IID each of the coordinates, and that's what I get. Okay? Take the log of that, this term will come back out. It's this term right here in the exponent that will come out, this will be just some other constant. So what I'll get is n g to d over d wg squared by p squared minus d plus 1 over 2 log 2 pi p squared. Okay. There's really not much going on. This is the squared loss term that we looked at last time, and there's another square appearing because of the Gaussian prior that you just put on the weight vector. Right? And that's sort of the key essence of what we're trying to do here. this was an argmax, so I'm going to convert it into an argmin because there's a bunch of negative sides all throughout. Notice that these are constants; they don't really matter with respect to W, so we can ignore them out of the argmax. And what you get is 1 through n yi minus W transpose xi squared plus 2 sigma squared by 2 t squared equals 0 to t W. Okay. The denominator got multiplied here, so there's some constant here. And here's the key part. What I'm going to also do is I'm going to multiply by 1 over n on both sides. And the reason I'm going to do that is, this is the argmax. Multiplication by a scalar won't really matter. Right? But the reason why I'm going to do that is then I can interpret this as average loss, right, or average error. This is the least squared fitting error criteria that we've been working with. And this, maybe you want to tell me what that is? L2 norm. So that's just the weight vector squared, right? That's just, and I'm going to call this constant some lambda, and so it's going to become lambda by n. Okay. So the key thing is that just as we started off doing maximum likelihood estimation and it resulted in minimum least square fitting, Bayesian estimation with Gaussian prior is going to lead to, we want good error, right? So we want low error on the training data. Plus, there's this odd term which doesn't seem to make sense. Error plus the norm of W should be small, multiplied by some constant. Right? Why would we want small norm? Why does that make sense?
You don't want your feature values to, your feature parameters to give too much of a weight on your data. So you want the majority of your number data with some.
Interesting. So there was the weight vector that was multiplied by the x, right? So W transpose x1 times x1 all the way to xd. And this was your prediction. Somehow we don't want this weight vector to have high norm. And why do we not want it? Because not wanting high norm is the same thing as saying we prefer it to be around 0. Why would we want that? So here's one way of thinking about it. We've come up with this objective function. To see whether the objective function makes sense, let's try pushing it to extremes. So what happens to this objective function as lambda goes to 0? Or which is
It becomes
exactly same as Emily. So lambda is going to 0 when your t squared, for example, goes to infinity, or an extremely large number. That's the variance sitting in the prior, right here. So if your prior is a Gaussian with extremely large variance, then it's nearly uniform over what it believes about different weight coordinates, right? So that part makes sense. If you have extremely large variance, this lambda is going to be 0, you're going to ignore this term, you're going to just do least squared splitting. The other thing that could happen is you could have an extremely large data set, n could go to infinity, right? And then this term would vanish as well. So that's not going to matter as well. Right? So that feels nice. So that prior, the effect of prior goes away as you see a large data set here. Right? That feels like it's doing the right thing. What about the other case? What if alpha starts becoming, or lambda starts becoming infinity? It's a really large number. Then basically what happens is your weight vector converges to 0, because this is the only term, this term dominates between the two, right? This term is between 0 and 1, or it's between 0 and the maximum error that you could make, right? It's just some upper scalar. This is a large constant, so you only care about this term right here. So your weight vector goes to 0, and so all your predictions go to 0 as well. So y hat goes to 0 for every single data point. So you start predicting 0, which feels a little odd. Right? Why should we do that? somehow lambda equals 0 would mean that, it should mean that we have extremely strong confidence in our priors. We should predict something sensible. And here's one thing you can do. You can change this loss, this norm to exclude the bias feature. So instead of starting from 0, you could start from 1. So in this weight times feature matrix, your score, it's W0 plus W1 through n transpose x1 to n. Where I'm sort of using MATLAB-ish notation here. These numbers you're penalizing that they should not be large. This number you don't care about. What will happen then if lambda is extremely large? There's something suggested. Mean. So first of all, these numbers go to 0, right? Because you can't have any magnitude of these numbers if lambda is infinity. But this number is essentially free, right? You can optimize this number, and the only thing that it can have an effect on is this loss function. So it's the same as doing least squares with not a single feature, right? You have no information about the data. I just give you y's. There is no x, and I ask you to do the best you can. The best thing you can do, and you can mathematically show it, is for W0 to just become the mean of y. So take your data set values and set it equal to the mean. And so once you do that, all of y hat will always be y mean. Right? That's what you'll predict for every, no matter what your input is, you're going to predict that because everything that multiplied that input is 0. That makes sense? Okay. So this behaves correctly. This is loss plus, this is the likelihood term plus some lambda times prior. You can also view this as loss plus something known as a regularizer. A regularizer is something that encourages your optimization procedure to pick a model that is in some sense simple. Right? This regularizer pushes you towards the mean. It encourages you to pick parameters where you set 0 to all the other parameters. You set 0 here, and you basically predict the mean value. Right? So this is a function that forces you to pick something simple. Okay. So the extremes are okay. How do we solve this minimization problem for any particular lambda? We can do that in a couple of steps. What?
Is it homework?
No, that's not homework 2. It's too simple for homework 2. It can be done in a couple of steps. So if I had to do it in one step, that would be homework 2. Okay. So here's the equation we want to solve. There's some loss term plus some lambda times the weight vector. We had already written this part out as 1 over n y minus xw transpose y minus xw. This was just the matrix notation for the loss function plus lambda by, oh I don't need lambda by n because I already have lambda times w transpose w. Right? That's the new term. Okay, I can take the gradient of this with respect to w, and I can set it to 0, and that's what we did for Emily as well, right? About least squares as well. So what do we get? Well, so this term right here, w x w minus 2 y transpose x plus lambda. Alright. Take the gradient. This term goes away. This w gets knocked out. So does this. So does this, and I get to write 2 in. Not there, but there. Right? That's just the derivative. This term vanishes. This is a quadratic term in w, so that vanishes and I write 2. That's a quadratic, so that vanishes and I write 2. Okay? and this just results in and I just set that equal to 0, the gradient. That makes sense? So what do I have? It's 2 W transpose x transpose x minus 2 y transpose x plus lambda by n W transpose equal to 0. That's just equal to x transpose y equals x transpose x plus lambda by n times identity of W. Right? This term plus this term now depends on W. There's a identity matrix to make sure I can do matrix plus. This is a matrix, this is a matrix, those two are added together to multiply into this vector, that's this. And so what I get is W hat MAP is equal to x transpose x plus lambda by n identity inverse x transpose y. So that extra term we added, right, compared to least squares fitting. This was least squares fitting. This is the extra term that got added. It shows up in the gradient and it shows up right here. It ends up adding an identity matrix to this x transpose x with a multiplier lambda by n. Right? So this is not a pseudo inverse. This is a modification of a pseudo inverse. Anybody want to tell me what adding of an identity matrix does to a matrix eigenvalues? What does it mean? If I start with a matrix A and it has some eigenvector and eigenvalue, what do I know about A plus identity? Lambda plus 1, not bad. A plus identity of x is ax plus identity x. You get lambda plus 1. That's right. So this operation, remember identity matrix is stuff that's on the diagonals. You're just adding, you take this dot product between your feature vectors and you're adding on the diagonal certain numbers. It's shifting the eigenvalues up. What happens when eigenvalues get shifted up? Eigenvalues become positive. So inverse becomes possible. If you had 0 eigenvalues before, you couldn't do the inverse. You've now shifted them up to a positive number, and so inverse becomes possible. Right? So this idea of adding identity to a matrix eigenvalues, to shift the eigenvalues up so that you can make this invertible, this is a really old idea. This is just linear algebra 101. But this process is a Bayesian interpretation of that idea. Right? What does it mean in least squares to add something? This is a hack, right? This is what you would do if you were writing MATLAB code and things crashed. Oops, it's not invertible. Let me just add, negative values, just shift everything up. What does that mean? It means that you're putting a 0 mean prior on your weight vector and whatever you had shifted, that's the strength of the regularizer or the prior that you're choosing. Does that make sense? Yes?
I was wondering, that lambda term, it's equal to the 2 beta squared and 2t squared.
Yeah.
But I guess we don't know the theta squared though, so that...
You don't know what theta squared is, you don't know what t squared is, and in some sense you don't care, right? Because all of this was nice, but in the end, you're going to have to solve this optimization. Like, you're just going to have to choose some lambda that's going to give you a result. If you have a large data set, it's not going to matter. If n is large, then you don't need to shift up the eigenvalues by anything. This matrix will already be nearly invertible. Right? If n is small, if you have a small data set, that's when priors start mattering. Then you can start asking the question, is this a good prior? Is Gaussian is what I should add, or should we add something else? Does that make sense?
I have one question.
Yes.
When lambda tends to infinity,
Yeah.
W vector goes to 0. Is that because your prior had a mean of 0?
Yes, that's
So
right.
if your
your
prior
prior
had a mean
had-
of different means
Yeah.
for the W1, W2, then W vector will tend to be that.
Exactly.
mean, right?
Exactly. So if your prior had some non-zero mean, it would have shown up in this equation right here. Right? So it would be a sub minus mu somewhere.
So if some features have a large magnitude in general, then the W for those would be non-zero. I mean, this would prefer those as compared to those features that are really small. So can it be taken care of by changing the mean prior for those features?
Yeah, so here we're making an assumption, right? The assumption we made was that the variance, right, the t is same in every dimension. You can either pre-process your data so that you normalize your data set, divide by some constant so that they have the same variance, or you can choose a different prior for every, the variance parameter for every coordinate in your prior, right? But in terms of what that would mean here, you would sort of not have a single lambda parameter, right? It would be different for every coordinate, and this would not be an identity matrix. It would be something that has the various weighting factors on the matrix. That makes sense? Yes. Okay. So just backing up, we did least squares. That led us to a pseudo-inverse type solution. You add a prior so that you can do Bayesian estimation. That also leads you to a pseudo likelihood like solution, except it has this nice interpretation of making the matrix invertible. That makes sense? Okay. This particular combination of using a Gaussian likelihood, so your y is generated by a Gaussian centered at the mean of W transpose X, and using the Gaussian prior, this particular combination is known as ridge regression. And just like extremely simple ideas, this was discovered multiple times in multiple communities, and it has different names in different communities. But the Bayesian regression estimation view of it is that it's a Gaussian prior with Gaussian likelihood. And you can change that, right? You can use different sort of likelihood functions, you can use different priors, and it would have different type of regression methods that you can come up with, right? So you could use a Gaussian likelihood with a uniform prior. We did that. That's what MLE was, right? Uniform prior, MLE, that's why it was called least squares, right? You can use a Gaussian prior with a Gaussian likelihood with a Gaussian prior. That was ridge regression. That's what the last slide was. You can use a Laplacian likelihood with a uniform prior. That's what we did with the robust least squares, right? Where we replaced squared loss by absolute, and that was robust regression. But you can mix and match. You can use Gaussian likelihood with Laplacian prior. You can use student-y likelihood with uniform priors, and you can have sort of different combinations of the likelihoods that you're putting and the priors you're putting to construct different methods.
What is student likelihood?
It's a different student-y is a different distribution, so you're assuming that y comes from a different distribution, which again has parameters like a mean parameter and a variance parameter, and the mean parameter is again some weight vector times the feature. Right, so once you view those two terms as these two values, we can mix and match. Okay, does that make sense? All right, so now let's talk about polynomial regression. So far, everything that we've said has been linear regression, right? There has been a model which was you collect some data, I multiply that by a weight vector, and that's how I regress. Let's say, for simplicity, you have one feature, x, right? It's only one value. This is what would be polynomial regression, right? Let's say you plotted your data, and it's clear that it's not a straight line. You'd like to fit a polynomial. You can do that, right? What we can do is, we can say W0, that's my constant term, W1, and I can start having x squared, x cubed, all the way till x to the m or x to the d, right? Some dimensionality. So this is an mth order polynomial, right? But it's polynomial in x. The key thing to notice is that it's still linear in w. So everything is still the same as linear regression, right? Everything we studied was, we developed the tools for linear regression, but we never actually specified linear in what. And this is going to be a common case. We don't actually care about being linear in our data. We care about being linear in our parameters. And if you notice, this is still linear in your parameters. Why? Because you can still take out a vector w0, w1 all the way till wm, and another feature vector, which is x, 1x, x squared all the way till x to the d. Right? So what we're going to say is that, so polynomial regression in, let's say in 1D for now, which means x belongs to R1, right? It's just one-dimensional feature. I can have polynomial regression, which just means w0 plus w1 x to the power all the way to wd x raised to power d. And this is the same thing as saying it's w transpose some phi of x. X is a feature, phi of x is a vector that takes a scalar x, right? So phi is a mapping, it takes a scalar from real to r to the d. Right? It takes a single value and it creates 1 x to the power 1, x squared, all the way to x to the d. Right? And this expression is linear in W and is linear in the new feature space that you're creating. So this is often known as feature augmentation. Right? You were given one number which is x, and you're creating new features which are in this case monomials of varying degrees. Right? And so if you can do that, then everything we've studied about linear regression still applies. Right? This is still linear in W. You can still construct a data matrix X. Only this time, it's phi x of 0 coordinate all the way till phi x of whatever dth coordinate is the length of this vector. Right? Does that make sense? In fact, this is all for a single variable. X can be a vector. Right? What stops me from making this capital D and making this little d? My input could be, for example, x1, x2, x3, some three-dimensional things that you measure, and my augmented feature vector can be, let's say, I keep the original, x1, x2, x3, and then I multiply all the pairs, x1 times x2, x2 times x3, x3 times x1. This thing, when multiplied by a weight vector, would just learn linear terms in x1, x2, x3. This thing, when multiplied by a weight vector, would learn linear plus quadratics. Right? In fact, I can augment it by x1 squares, x2 squares, x3 squares. Right? And if you just reshape things, you can see in your head that you can express this same quantity as x transpose ax. Right? It has all the quadratic combinations for a particular vector. Right? But in terms of this feature vector, phi of x, everything is still linear. Right? Does that make sense? So think of this process as an embedding. It takes an input data and it embeds it in a higher dimensional space. Right? And we're going to come back to this idea lots of times, especially in the context of support vector machines and other sort of neural network type classifiers as well. That what we're actually going to be interested in is how do you get this embedding? What feature space do things live in so that you can then do nice linear processing? That makes sense? Okay, let's take a look.
Okay, that's what I thought.
这一条是蓝的，这一条是蓝的，这为啥要干蓝的点呢？标准是这儿蓝的，这儿蓝的，
Except it doesn't do that. It looks at something called an
What do you have a payment relationship?
Somebody just mentioned that there may have been a bug in somewhere in my derivation. It should have just been lambda, which was multiplying the identity matrix, not lambda by n. I'll go back and fix it, and you'll find it in my notes when I Alright, but coming back here, so we're talking about polynomial regression in one dimension, and in this case, the sort of embedding or the feature space that you're creating is just a set of monomials in this one-dimensional vector. So you can still construct that data matrix, only this time the data matrix. So if you were just doing linear regression, this stuff would not exist. If you were just doing linear regression, this is all that your data would be, and you're augmenting your features by adding the monomials. And so you can still construct this data matrix, and you can still use that exact same expression, only now your dimensionality is much higher. Does that make sense? And as I mentioned, you don't want to go too high in terms of dimensionality, otherwise this will not be invertible. You just won't be able to do this. Okay, and you can do the same thing. You can think of this as W0 times W1 of this. In this new embedding space, the first coordinate of that, the second coordinate of that, the mth coordinates of that. And this can now look at the entire vector x. It doesn't just have to look at one dimensional. X can be a vector, right? And you still get the exact same expression, only now the design matrix has the phi 0th coordinate, phi 1th coordinate, phi 2th coordinate, all the way to phi n. Does that make sense? And once you construct the design matrix, the expression is identical. Okay.
time, show what that looks like. Alright, so here's a quick demo of that. So here's me creating a data set with a particular intent in mind, and here's the linear regression. So this is X, this is Y, right? This is the first order fit to it. You can ask for a 0th order fit to the thing, and let me do that right. Okay. So now I can ask for a, can I ask for a 0? Yes. So this is the 0th order fit to it. This is just, X to the power till 0, right? So you just get one parameter W0, and the best thing you can do is look at the average Y values and just fit that. This doesn't depend on X, it just predicts the same thing. This is linear regression in one dimension, slightly better. You get a slope of that line. It's still an extremely poor fit. This is linear regression in 2 dimensions, slightly better, right? You get somewhat of the trend of the data. You can see the data points, and you can see sort of how far things are. And so there are still some residuals, right? You can look at this point is far away from where it's actually projected by the curve, and so the sum of these squares is still a large value. There is no regularization here. This is just minimizing these squares in this thing. Okay. But why stop at 2? We can go to a 3rd dimensional fit. We can go to a 4th dimensional fit. Doesn't seem to be working well. Let's go to a 14th dimension. Okay. Why is this not the right answer? It seems to work perfectly, right? Let me 13th dimensional fit. Oh, actually that misses. 14th, perfect. Why is this not the right answer? Overfitting. So the idea is that this perfectly explains the squared error in this case is 0. This curve passes through every single point in the training data set. It actually has, it's a 14th dimensional curve, so it has 14 sort of roots of, if you could get the roots of this. But this is not what we expect as the right answer if you had some sort of priors on what to expect out of this, right? And if you imagine, if you add a prior that bias yourself towards the 0 vector, the 0 vector just always predicts this, right? If you don't, this is the absolute 0 vector. If you don't penalize sort of the mean value, does that make sense? So you're sort of adding a push towards this solution. Okay. So this is actually a good segue into a topic that's called model fitting. If I give you a data set, and the way you're actually fitting parameters is by minimizing least squares on training data, then what basis do you use to reject this as, how do you identify that this is overfit? How do you know this is not a good solution? Yes?
If it fails in predicting new data.
We don't have new data. I gave you data, you used all of it to find W. Use your priors.
So if it's not very similar to your prior.
If it's not very similar to your prior, so I guess what you're saying is, look at this is the W, I guess, that is learned. These are extremely large magnitude values. I don't know if these are W's, by the way, or not, but if that was the large magnitude values, they're extremely large, you're probably overfitting. Is that the idea?
The number of features is greater than the number of data points.
So the number of features is greater than the number of data points. In that case, you'll actually get a perfect fit, right? You'll be able to explain everything. So what if that's not the case? What if you're close to the boundary, but that's a condition that you're checking?
Still do the cross validation things, like partition the points to some part, use one part to train and predict on the second part.
Exactly. So combining it with what Chris was saying, right? This is exactly what the idea is, that you don't actually care about how well this does on the training data. What you care about is how well does this does on new data that you haven't seen before. And the way to simulate that is when you have a data set, you split it into something called train and something called val, or a validation set. And you're learning your parameters only on the training set. And you will learn parameters for the 0th order model, the 1st order model, the 2nd order model, all the way to the 15th order model.
and you will use those parameters to test their predictions on the validation set. Right? And you will look at the validation error to decide between these model classes. The key thing to understand here is that this 14th order polynomial is the space of all vectors, is a space of all vectors in R to the 15, right? So 0th order, 1st order, all the way to 14. That space contains a 10th order polynomial in it. All I have to do is set some zeros and some coordinates, right? So these model classes are actually nested. Does that make sense? If you recall, we've been talking about something called a model class, right? Or a hypothesis space. Hypothesis or model class. Your 15th order polynomial is a particular model class that contains in it every point is a vector in, let's say, R to the 15. I'm ignoring the bias issue here, right? But these model classes are completely nested. The 15th order model class contains in it as a subset the 14th order model class, which contains it as a subset the 13th order model class, all the way to the 0th order model class, which is a completely zero vector. Right? I can get this point here by having the first 14 values and the 15th value set to 0. And we said least squares or learning was optimization or search in this model class. So if you use a larger model class, by definition, your training error can only go down. Right? If you're searching for the first order fit, you get something. You're searching for the second order fit all the way to the 15th order fit. By definition, if I start plotting on this axis the polynomial order b, and this is, let's say, error, your training error can only go down. It will go down to 0. You'll start off with some high error, and at some point you would have explained everything. But this is not indicative of how well you will perform in a test set or a new data point. Right? So, in order to understand that, what we actually care about So this feels a little dissatisfying because it feels like you wrote down an objective, we were minimizing that objective, but somehow if I do better on that objective, I'm worse off, right? So this feels like there's something that got missed off here. Why did that happen? It's because this is actually not what you care about. Training, train is not actually what you care about. What you care about is something called expected loss. We said that X and Y, your data, are samples coming from some distribution. We don't know what that distribution is, but we can get the samples. What you actually care about is, on average, if someone computed this expectation of the loss function of Y compared to Y hat of X over W. Right? If you were given an X, and you chose a particular model class and a particular parameter, and you made a prediction, here's the loss of that prediction, and if you could compute the expected loss over all possible X and Y, this, if that would be small, that's your goal. Right? This is what we want to min over W. Right? We want to optimize this. And this is the same thing as saying, this is some fancy integral over the space of X, over the space of Y. It's loss of Y over Y hat X over W times df of X over Y times dx dy. Right? This is double integral, just writing down what that expectation is. And then you're supposed to minimize this over W. Why is this a hard problem? Anybody want to tell me? your data comes from some probability distribution. This is the expectation of the loss that you're making over that probability distribution, just the definition of expectation. If this was low, you'd be home free. If you could really just do this minimization, if you could find the one thing, that one parameter setting that could minimize over all possible samplings of the data set, right? This is an expectation over all possible samplings of the data set. If this could be small, we'd be done. We can't do this because we don't know what P is, and we don't like integration. And minimization of integration is really difficult. Right? This is really hard because we don't know what we're optimizing. Even if we knew, we made some assumptions about where the data is coming from, this would be a difficult integration problem. That's not what you care about. You actually care about minimization of an integration problem. Right? So that's out. And so what you do is you replace this double integral with samples. Right? So I'm going to remove the minimization part. But you basically say, I'm actually not going to care about the expected loss. I'm going to replace this by a sampling procedure. That's why x and y, a data set of x1, y1, all the way till xn, yn, are actually sampled from this distribution, and I'm going to just compute the loss of y1 to y hat. I'm just going to compute this loss and take the average of that, and that's going to be a good approximation of the expected loss. Right? This is what we're doing when we do least squared regression or any other loss function that we're going to do. We actually care about this expected loss and we're minimizing this. Okay, so with that view, why does minimizing this not work? So far it feels like it's still doing the right thing. It doesn't work because when you're given a data set, here's the usual procedural view of things. You divide it into train, you divide it into val, and you divide it into test. Train is, these are rough numbers. Usually this is something like you'll split off 60% of the data for train, maybe something like 20% of the data for val, maybe something like 20% of the data for test. Right? The goal of the training set is to estimate this W. Right? You're trying to minimize, there are some weights, and the goal of this is to argmin of loss of W, right? Of, let me say, E train. The goal of the training data set is to fit your parameters by minimizing the training loss. The goal of the validation data set is to choose hyperparameters or model classes. So in this case, D is going to be argmin of D from 1 through 100 or something of the validation error of W hat used on training. Right, so you're going to minimize training error to fit W, and you're going to measure the error that these parameters are making on new held out data set, and you're going to use that to do model selection. This is model selection. Your models are actually nested. So by definition, the largest model will work the best on training data. You cannot use training data to choose both this parameter and this parameter because there's a nested relationship. You will always use a larger model class. And then the goal of the test set is only to estimate this. Right? There's no optimization happening. The goal of the test set is only to do this approximation. How well am I going to perform when I ship this product out into the world? Does that make sense?
So during training, you use all the models? So we don't know what models are available.
Yes. So during training, you would have to train multiple models. Then you would have to evaluate the performance of those models. In this case, it was a nested model class from 0th to 2nd. But you could imagine that it could not be nested. So your decision could be between, I need to train a linear SVM versus a kernel SVM versus a neural network versus a decision tree. Right? Some of those have nested relationships. For example, the linear versus a kernel SVM, depending on the kernel you use, but some of them don't have nested relationships. The kind of functional mappings that the decision tree can learn may actually have some intersection, but may not be a nested intersection. Does that make sense? All right. So at this point, we've finished least squares, and we've moved on to this new topic of model selection. And this is the idea of, this idea of model selection also shows up when you ask these questions, how do I pick hyperparameters, or how do I do feature selection? If you think about it, feature selection is the same thing as model selection, where you're defining a model class, you're constraining that this weight vector will, according to for this dimension, will always be 0, right? So you're slicing your hypothesis class into a bunch of sub-hypotheses, sub-model classes, right, by dropping various features. And then you're asking which one of them is a better one. Okay. It's important to keep this in mind. I cannot stress this enough to people coming into machine learning as a new area. Reporting, training errors are good only for you to do diagnostics. They're for you to see how well you're doing on training set versus validation set versus test set. Training errors are not supposed to be reported as how well your method is working. And that's a big no-no. And the other big no-no is you cannot ever optimize parameters or test them. Because at that point, the estimate that you have, you're using a test data set as an unbiased estimator of how well your method will perform when you ship it out. If you have tweaked parameters, if you performed an optimization, then it is no longer an unbiased estimate. Right? Then it is a biased estimator. Then that number that it is giving you is an over-optimistic number. You're not going to get that performance. Does that make sense? Okay. In a lot of cases, often you don't have enough training data to actually split it into a train, val, test set. Let's say you just have 100 samples, and for example, in the senator dataset case, we've maybe given you 60 and we've held off 40. You don't even have access to those. If you take the 60 and if you start dividing them into subsets of 3, you'll run into this problem that your training set size is just too small. Right? So one thing that you can do to overcome that is this idea that you've already seen is cross-validation. You would take your data set, you would break it up into chunks of n, or chunks of n-fold cross-validation, or k-fold cross-validation. You would break it up into chunks. You would hold off this part, consider this as train, this as val. So you would go ahead and train your model, a single one or multiple ones, on this training set, and then you would make predictions on this held-off set, right? With one model or multiple models that you're training. And then you just repeat. So you repeat, hold off and take a different fold all the way to the kth fold. Right? And at this point, you have made predictions on this entire data set of size n, but every time you made a prediction, it was coming from a model that did not see the sample. And so you've essentially used this entire data set both as train and as val. But you've done it in a clean way. Does that make sense? Okay. And the extreme case of this is what is called as leave one out cross-validation, where the size of the fold is just one data point. So leave one out cross-validation is when you take one sample out, you're learning on n-1 samples, and you're making prediction on this one. You put it back in, take something else out, and notice that you have to train your models n times if your data set is n, size n. Right? And all that changes between the models is you take one data point in and put one data point in, take one out. Right? Other n-2 are exactly identical. They haven't changed. But so that's why you can actually sometimes come up with fast tricks so that you go from one training to another training with extremely efficient updates. In fact, in homework 2, that's what you're doing. You're doing leave one out cross-validation for regression, and you're showing how to do that in essentially the same time as one regression call. Right? Instead of having to run pseudo-inverse n times, take one point out, run pseudo-inverse on the n-1 points, put it back in, do it again, you're basically showing that you can do it with a single pseudo-inverse. There's a little bit extra that you have to do after that, but in terms of asymptotic complexity, it's the same complexity. Right? So sometimes it's possible. You can do it. Okay. Let's see. So we were talking about training error and so we talked about this plot, right? That if you keep increasing complexity. So on the x-axis, let me just say it's complexity. As you use larger and larger model classes, right now we're talking about linear regression or polynomial regression. So D is a nice integer that you can plot on the x-axis, but in general the x-axis will be anything called complexity. You could take different model classes, maybe they're not nested, and if you set them up this way, you will generally get a trend like this. But that's not what you're going to care about. You will also have another plot, which is validation error. So how well are you doing on that held out set of validation? Trained on this, tested on this. Right? That plot will usually look like this. Usually, it will not be pretty. It'll, you've drawn this for k-nearest neighbors, but generally there will be a trend somewhat like this if you play with the axes enough. If you want to see the trend, you will find it. But okay. So it'll usually look like this, and there will be two sort of regimes that we can talk about. There's sort of this regime where both the training error is high and the validation error is high. And there's this regime where the training error is going to be really low, but the validation error is going to be high. Right? This regime is going to be the underfitting regime. This is when underfitting. Right? This is when you're using a model that is too simple for your problem. You're not doing well on training data, you're not doing well on test data. Remember, training data is what you're optimizing to find the best parameter in the model class, right? Even the best parameter in the model class just cannot give you good performance, right? This regime, on the other hand, is when your model class is large enough, you can actually find something that does really well. You solve this optimization problem really, really well. You can write this down to 0. But at this point, your model class is so large that you are overfitting, right? And your performance on validation set, which is the held off set, is really poor. This is what was happening in terms of the polynomial regression curves that we looked at. You got 0 least squared performance, but you can all sort of imagine that that's not where the data came from. It's not from that 15th order polynomial, right? And what makes it tricky often is the difference between a large model, large complexity model, and a small complexity model is sometimes often all relative to the size of training data that you have. If you think about it, in that polynomial fitting case, the reason why we got 0 training error is because there were only 14 points. If I had sampled infinitely many points, it would not have come up with that 14th order polynomial, right? So we drew the nested model classes, right? There's the 15th order polynomial, the 14th order polynomial, and maybe the data came from a noisy version of a second order polynomial. Notice that the 15th does contain a second order polynomial in it as a special case, right? So what it could learn is that, put some weights on the top, on the first two, W0, W1, and actually set everything else to 0. It can actually learn that, right? But it's not going to end up learning that because the number of samples it sees are too small. Right? If it did have infinite data, you could actually get validation performance small as well. Does that make sense? So we're going to be always trying to check these two regimes. Are we underfitting or are we overfitting? If you're in the underfitting regime, and you can easily check that, if your training error is high and your validation error high, what makes it somewhat difficult is it's often domain dependent what high and low are. Right? What is unacceptably high error versus unacceptably low error? But if both those things are large, then you know that you need to do something to increase the complexity of the model class. You need to add new features, you need to try different kernels, you need to go to a richer model class space. If you're in this domain where your training, it's working really well, you ship it out, on validation it's not doing well. That's when you need to scale back a little. You need to do feature selection, you need to do dimensionality reduction. You need to shrink down the size of your model class because you're overfitting. Right? And a simpler model class will do better somewhere around here. Right? And often, that's why validation curves are often used to choose what size of model class should I choose and what D should I use. Does that make sense? Overfitting, and here's a visual sort of illustration of what we've been talking about. You can almost always break performance on held out set or expected loss into two or three different sources of why you're making error. Right? If you write something down and it's not working well, you often need to debug why it's not working well, because just because it is not working well doesn't immediately tell you what to do. Often you need to know what type of error you're facing so that you can make certain changes. And it's useful to keep sort of this sort of picture in mind. So here's the picture, right? This is what I drew some time ago. There is reality. Reality is the true mapping that takes in an image and gives you the correct output. True input to output, the correct mapping. Right? I work in computer vision, so I think like this. Right? Input is an image, Y is some segmentation or recognition of everything that's in the image. Okay? This is your model class. Reality is not going to be in your model class, right? You wrote down some sort of model, don't worry about what it looks like. This could be whatever, linear classifiers, nonlinear classifiers, regression, whatever. Right? Usually reality is not going to be part of your model class. And usually your goal is going to be, find me the best thing in the model class that minimizes some error. Right? Find me the best thing, get me the closest to reality. And that error is going to be modeling error or approximation error. Okay? That's the error that you made right off the bat because you decided to go with naive Bayes or logistic regression or decision trees. Or you decided to extract these 10 features and not something else. Right? That's right off the bat, that's the error you have to make. Then but that's not the only error, right? There's a second source of error. That's the statistical estimation error. That's the error between the best thing you could learn if you had infinite data versus what you actually end up learning because of finite samples. Right? So that's what you're losing out due to estimation error. You only have n data points, n is small, the number of parameters you have to learn is large, so it's an under constrained problem. There are many things that satisfy the same things. Right? So that's estimation error. But that's not it either. There's a third source of error, and the third source of error is optimization error. Right? What you actually want to minimize may be a non-convex objective function. And so what you end up, so even with n samples, where you end up landing in this model class may be different from where you could have landed if you solved a NP-hard optimization problem. Right? So far, we have not dealt with optimization error. Everything we've done has been nice and convex. I've written down first order gradient method, closed form solution, we've been able to reach here. So far, the only errors that we have to worry about are what was our model class, what is the modeling error, what is the estimation error. Right? But as we go to richer and richer model classes, there is going to be an optimization error as well. When you choose a smaller model class, for example, you drop some terms out of your model, you make it a lower order polynomial, it reduces the size of your model class, and therefore it increases modeling error or approximation error. Right? Now your model is a poorer approximation of reality, and so you have to pay more errors. However, because it's a simpler model, it has fewer parameters. Right? So estimation error shrinks as well. And maybe what you also dropped was the non-convex part of it. And so maybe optimization error also vanishes. Right? So there's a natural trade-off. You could make your model class larger, and then that would be a really, really great model. Right? This is a nearly perfect fit to reality, except we can't find it. It takes a million data points to find it because what we end up finding is here, and it's an objective function we can't optimize, so we land up here. Right? So there's always a trade-off between these three kinds of errors that we're making. There is no single machine learning model, right? There's a bunch of models where these three trade-offs will play off differently. That makes sense? And that's kind of one of the reasons why we have to teach you about all the different kinds of tools, because they may be better suited for the kinds of problems that you're solving. Okay, and here's something to keep in mind. Approximation error or modeling error is you approximated reality with model. Estimation error, you're trying to learn data, you like to learn your data with finite data, that's why learn your model with finite data, that's what caused estimation error. Optimization error was either you were lazy or you just couldn't optimize it to completion, right? Or you said, I have some budget constraint. I'm only going to run it for X number of hours, and whatever you end up solving at that point, that's my model. That's what I'm shipping. Right? So that's optimization. And next time, we're going to talk about something called Bayes error, which is reality sucks. Like for the same input, you can actually have two different outputs. You can have infinitely many data points. You can solve NP-hard problems, But sometimes, that's the concept that I'm trying to teach you, that for the same x, there's two different y's possible with some probability. So no matter, even if you learn that concept perfectly, you are going to make some error in expectation. So those, we'll have to keep those in mind. Okay, let's stop here, and next time we'll pick up from